Hello students, now we will be discussing the first problem of ISI 2023 UGB, and this was from number theory and it is one of the toughest problem of the paper. This question consists of many concepts of number theory including the greatest integer function, number of digits in a number and inequalities. Now this was a very complicated question and solving this took a lot of time. So let us start this one. We have to determine all integers n such that every power of n has an odd number of digits. So we must first know that number of digits is given by greatest integer of log n base 10 plus 1. This is how we give the formula for number of digits. Now, how do we derive this? So, we observe that between 1 to 9, each number has one digit. Between 10 to 99, each number has two digits. Between 100 to 999, each number has three digits. So, we see that each of these numbers is between 10 to the power a minus 1 and 10 to the power a. So that gives us the insight of taking this greatest integer of log n base 10, because that a is given by log of a number base 10. So this is how we obtain this formula. Number of digits is by greatest integer of log n base 10 plus 1. Now let us start the problem. We need to find all n such that greatest integer of log n base 10 plus 1 is an odd number. So this implies greatest integer of log n base 10 is a even number. So now we have two cases. So case 1 is that n is of the type 10 to the power something, 10 to the power L1 multiplied with some constant, say k, 1. So putting this here we get, and since we are talking about power of m, so here it will be log n to the power m base 10, log n to the power m base 10. So now we get that greatest integer of m times L1 plus log k1 base 10 is an even number. So we get that m times L1 plus greatest integer of m into log of k1 base 10 should be an even number. Now if this is the condition, then if this is an even number, don't do it like this. Okay. We go by other method. Instead of multiplying a constant before, we will multiply it afterwards. Okay. Let me explain. First we take simply n as 10 to the power of l. Okay, we take n to be 10 to the power of l. So we get greatest integer of m times log 10 to the power L base 10 should be even, should be a even number. So this implies that m into L should be an even number for all m belonging to naturals. And this is possible when L is an even number. So L should be of the type 2k1. So every number, so every number of the type so every number of the type 10 to the power 2k 1 satisfies the condition. So every number of the type 10 to the power 2k1 satisfies the given condition. Okay, so this was for the part where uh, n is of the type 10 to the power n. Now we will consider the case 2 when n is not of the type 10 to the power of n. Now this one is the interesting case. So now when n is not of the type 10 to the power L, so this means greatest integer of this now becomes m times log n base 10 should be again an even number as in the previous case. So this means that 2k this should be the case with us. So this implies that n lies between 10 to the power of 2k by m to 10 to the power of 2k plus 1 by m. So n belongs to 10 to the power of 2k by m. N belongs to 10 to the power of 2k by m, 10 to the power of 2k by m plus 1, and so on till 10 to the power of 2k plus 1 by m minus 1. These are all, and we know that n is also natural number. So if these all are natural number, then this surely implies that 10 to the power of 2k by m is a natural number. And if 10 to the power of 2k by m is a natural number, then this implies that m must divide k. And m divides k means k is of the form k1 times m. K is of the form k1 times m. So if we now put it in the original in this set, then n belongs to 10 to the power of 2k1, 10 to the power of 2k1 plus 1, 10 to the power of 2k1 plus 2, and so on till 10 to the power of 2k1 n belongs to, sorry, really sorry for this. Actually, the plus 1 plus 2 comes down, not up. So n belongs to 10 to the power of 2k1, which we have already considered, 10 to the power of 2k1 plus 1, 10 to the power of 2k1 plus 2, and up till 10 to the power of 2k1 plus 99. So all the numbers of these forms also have odd digits for every power they are raised to. So overall, the final solution is n belongs to. So the solution, this is the solution. This is the final solution. In this set, n belongs. Now this was a pretty tough problem, and reducing this problem in examination hall, if you don't know this formula, is completely impossible. If you know the formula, still making so many equations is a tough task to do. So I hope the solution is clear. I will explain it in brief once again. I used the formula number of digits is equal to greatest integer of log n base 10 plus 1. Then I set up the equation and I get that greatest integer of log n to the power m base 10 should be even. And this is true for all m belonging to naturals. This is the most important time in the problem. That this condition should hold for all m belonging to naturals. So we take two cases. Case 1, n is a perfect power of 10, and case 2, n is not a power of 10. So if n is a power of 10, then n is of the type 10 to the power l, and l must be even. Since m times l is even for all m belonging to natural, so this means l must be even. So every number of the type 10 to the power 2k1 satisfies the condition. Case 2 is that n is not equal to 10 to the power of l. So we made this type of case, this equation, and from here we have that n should belong to this set 10 to the power 2k1, 10 to the power 2k1 plus 1, and so on till 10 to the power 2k1 plus 99. That is the up to modulo class 100. Okay, since it is 10 to the even power. So, and yeah, there should be one constant L multiplied, which is less than 10. Okay, so L into this L times 10 to the power 2k1 plus 1, L times 2 to the power, and L times 10 to the power 2k1 plus 2, and so on till L times 10 to the power 2k1 plus 99, where L is less than 10. So this concludes the problem, and I would say that this is a very tough problem. Thank you guys for listening patiently.